Let's have a look at an optimization problem. Quite commonly we use quadratic functions to model a problem. So when we're looking at an optimization, we want to typically know the maximum or the minimum of what the function will reach. And we've talked about the nature of a curve before now, that where a is greater than 0, the curve will have a minimum. It will be concave up. And where a is less than 0, it'll have a maximum. It'll be concave down. Now we use this idea of finding the minimum and maximum from the turning point to find out when the function will be at the y value will be at its greatest or at its smallest. The other thing that we need to consider is that when we're modeling a problem, typically we won't need the whole domain. We might just be looking at time, where time's greater than 0, or height, where height's greater than 0, or something like that, and that will restrict either the domain or the range of what we're looking at. And the maximum might in fact be at the extremes of the bounds rather than just the maximum or minimum. So here we'll look at an example that shows some of that. So we're building a fence against a wall. We want to find the maximum area that we can make inside the pen, given that the amount of fence that we have is 20 meters. Now, the wall is long enough that that's not going to be a factor. The fence will just be here, here, and here. So we can write a formula for the fence line. We know that that length plus that length plus that length must equal 20, or 2 times L plus W equals 20. So the width must always be 20 take 2L. We know that the area of the pen is just going to be L times W. So once we know that, we can substitute in W into the equation to get the area in terms of the length alone. And if we multiply this out, though this equation is in factored form, we could get it in standard form by saying 20L take 2L squared. Now, looking at this equation here, because it's in factored form, we know that it's going to cross the x-axis at 0, or when 20 take 2L is 0. 20 take 2L equals 0 would be 2L equals 20, L equals 10, and that's this point here. Now we can get that just by looking at this equation here. I did it by inspection, though you could have solved that to equal 0 using null factor law. So the turning point is going to be at halfway between these two values. So at L equals 5, 10 plus 0 is 0, divided by 2 is 5. And if we substitute 5 into the equation, we find out that the maximum area is going to be 50. Now we can check the bounds, and we can see that if we went beyond 20, the area would be negative and reasonably irrelevant, and the same with less than 0. So the bounds aren't important in this case. We know that the maximum area is going to be at length equals 5, t equals 20. We can find the width by substituting the length back into the width formula. So 20 take 2 times 5, 20 take 10 would give us 10. The dimensions of the pen will be 5 this way and 10 that way, as stated here. It's always important to actually state the answer to the question. Now, funnily enough, this question didn't ask the dimensions. I stated them anyway just to be sure. Here's a second problem. This time we've got ice cream sales per day is sales equals x squared take 10x plus 35. Actually, that shouldn't be x, that should be t, so I will correct that. Just to get used to working with x's and y's. Take 10t plus 35. I'm going to have to be doing this all the way through, I think. T squared take 10t. T. Right, I did it right everywhere else. Okay. So where S equals the number of ice creams sold, and T equals the month of the year, with T equals 0 being January. So January, February, March, April, May, June, July, August, September, October, November, December, noting that they don't relate to the normal numbers that we associate with months of the year. July is not 7, in this case July will be 6. So, because A is positive, we'll have a minimum turning point, which we have here on our curve where I've graphed it. And we can complete the square for this function, halve that, square it, subtract it, add that, find out that the maximum's 10. The minimum's 10. And it happens at t equals 5, which is correct. So we know minimum sales happen at t equals 5. That was nice and easy. And that was what this question was, find the minimum. Now the next question is find the maximum. Now we can see the maximum if we went behind January, which we're not interested in because we're only interested in 12 months, it would go higher. And if we go past 11, it would go higher, but we're only interested in the domain from 0 to 11. And from our graph, we can see that it's not at 0, it's actually at 11. It's definitely not at the turning point. So let's check the boundaries. So at S0, the y-intercept, the number of sales is 35. And at S11, by substituting in 11 into the equation, we find that it's actually at 46. That tells us the maximum occurs at t equals 11 in December, in the hotter months of the year. Now, is it more likely that the geographical location is north or south of the equator? This requires us to think about the information we've been given. And we'd assume that it's in the south because the south has its cooler months in the middle of the year, whereas in the north it has the cooler months in December, in January. We'd expect the graph to be upside down if it was north. So there you go. An application of quadratics into common circumstances. Thank you, everyone.